You'll get a chance to practice that some more on your homework, okay? In the last few minutes, I guess, maybe 10 minutes that we have left, I want to introduce separation of variables, right? So you may have seen this before, right? And so I'll just start with sort of a warm-up problem. You can kind of work along with it if you wish. This may be familiar to you. You may have seen it before, right? So let's go back to the bounded heat equation problem that we wrote down before and we proved uniqueness for, but we didn't really talk about how to get solutions to, okay? And so in the case where we have an initial boundary value problem, right, we're going to have these three sets of conditions, right? The idea with separation of variables is that you look at this problem and you say, well, maybe something I could guess that would be a solution is a solution that's just a product of the of a function of x and a function of t, okay? And if I substitute this in and I find an ODE for V and W, okay, with ICs or BCs, right, then maybe I can make some progress towards getting a solution, okay? So what happens when I do that, okay? So if you want to try that on your own, you can, pause the video and see how far you get, okay? I'm going to dive into the solution right now, okay? All right, so if I just plug this assumption in, right, I immediately see that if solutions are of this form to this PDE, okay, then the separated solution should satisfy this equation. Now, this is a single equation, and yet I have two unknowns, okay? But, if you've taken the prereq for this class, you know that you can separate out this equation into the parts that depend on just W and the parts that depend on V, okay? And because I know that V is just a function of X and W is just a function of T, I have a function of X and a function of T that equal each other. Now, the only way that can be for all X and T is if they're constant, okay? And so the trick is that I can make two equations out of one by saying, well, these must be equal to a constant. Let me call it minus lambda, okay? And why the minus lambda, okay? I'll just say that we'll see, okay? You could take positive lambda, okay, and it would work out fine, but it turns out you should expect that to be minus in this case because of the types of ODEs that are going to come out, okay, looking ahead. So what do I do now? Well, I take my, my X equation, right, and I pair these two sides together, right? I'm going to multiply through by KW, and I get, this is the T version of the equation, of the X version of the equation. So the T version of the equation, right, I get W prime of T is equal to minus K lambda W of T, okay? And the X version of the equation, right, I compare with the minus lambda, and I get V prime prime of X plus lambda V of X is equal to 0, okay? And remember, I only have one condition that is an initial condition, okay? And that's going to eventually apply to my time-dependent solutions. But I have two boundary conditions, right? They're just both, U of 0 equals 0 and U of L equals 0, okay? So this will have boundary conditions associated with it. And I can also refer to this as an eigenvalue problem, okay? So what are my boundary conditions? Well, I get V of 0 equals 0 and V of L equals 0, right? Because I have that U of 0t equals 0 and U of L equals t equals 0, right? So U of 0t is equal to W of t times V of 0 is equal to 0. So either WT is 0, in which case I get a trivial 0 solution, or V of 0 equals 0. So that's where I get this. U of LT equals W of T, V of L equals 0. So either V of L equals 0 or W of T equals 0, which would be a trivial solution. So I get V of L equals 0, okay? So now this is my boundary value problem. And this is my time-dependent problem here, okay? Okay, so what are my solutions, right? Well, this is just a standard second-order differential equation, okay? I won't go through the steps of solving it, right? You can look that up in your ODE textbook, right? But essentially, right, this should have solutions that look like V is equal to C1 cosine of square root of x plus C2 sine square root of lambda x, okay? But then the boundary conditions, what they tell me is that V of 0, which is equal to C1 equals 0. So this part goes away. And then V of L is equal to C2 sine of square root of lambda. L is equal to 0, which can only be the case if lambda n is equal to n pi over L quantity squared, okay? So that is my set of eigenvalues for n is like any integer value there, okay? But we'll restrict it to the natural numbers because the negative, the 0 is trivial, and then the negative numbers are just reflections of those sine functions, okay? So what we have at the end of the day, right, is that our solutions, right, are of the form Vn of x is equal to sine of n pi x over L, and lambda n is equal to n pi over L quantity squared, for n is in the natural numbers, right? So 1, 2, 3, 4, 5, so on, okay? Now, what about my time-dependent ODE? Well, that just has exponential solutions, right? So assuming, you know, for the time being, I don't have any initial conditions. Let's just set the prefactor constant equal to 1, right? And for each particular value of n, I'm going to have a different Wn, right? So I have this infinite set of solutions to my ODEs that go together, right? So in total, right, I have Un of xt's, okay, which are going to be Wn of t times Vn of x. And this is going to be e to the minus k lambda nt sine of n pi x over L, okay? Where my lambda n's are given here, okay? Now, just as an aside, right, what about, right, the lambda less than 0 case, okay? Well, basically, we end up excluding the solutions of the form v equals e to the lambda x, or square root of lambda x, e to the minus square root of lambda x, or e equals ax plus b, essentially because of the boundary conditions, okay? And you can see that for yourself, okay? That essentially there's no way to basically have v0 equals 0 and vl equals 0 with any with either these exponential functions being combined together or these this linear function here. Okay, you'll just get a vanishing trivial solution. Okay, so that means that these are the only solutions. Okay, for these particular boundary conditions. Okay, and that tells me then that by the principle of superposition, okay, I can do the following. I can just add them all up, right? So remember that it just holds for the natural numbers. So I have a natural way of indexing. I have some free constant that I can use to scale. And I'll go ahead and plug in my eigenvalue here, n pi over L squared, okay, t. And the last thing that I have to do is I must satisfy the initial condition, okay? And that initial condition is u of x0 equals some function f of x. And if I plug in t equals 0 here, this just becomes 1. And so I get the sum from n equals 1 up to infinity, bn sine of n pi x over L. Okay? And so what do I have here for my very last step? Well, I have a need for Fourier series, right? And so in order to construct these series solutions, right, I need to recall the theory of Fourier series. And what did Fourier series essentially tell me? Okay. The theory of Fourier series says that for any continuous function, or actually even any piecewise continuous function that is either defined on a bounded domain or it's defined on an unbounded domain and it's periodic, I can construct a Fourier series approximation to that function that will be exact if that function, say, C2, and if it's piecewise continuous, it'll be, like L2 accurate, essentially the integral difference squared of those functions will be vanishing. Okay. The Fourier series says that essentially for f, some function that maps the real line to itself, if it's periodic with some period L, okay, then essentially f of x equals a 0 over 2 plus the integral from n equals 1 up to infinity an cosine n pi x over L plus bn sine of n pi x over L, okay, where the way that we get these coefficients is that an and bn are equal to 1 over L, the integral from 0 up to L of f of x integrated against either cosine of n pi x over L or the sine of n pi x over L, integrated with respect to x. Now in our case, right, we just have the signs left over. Why is that okay? Well, because we know that our function should vanish at the boundaries, okay? So it's perfectly fine that we only have the sine functions in this case, because our function needs to satisfy these boundary conditions, okay? Now, on the next lecture on Wednesday, I'll talk about essentially briefly how you get this formula, right? I mean, you can just essentially check this formula yourself by just, integrating trig functions each other and noting that they're orthogonal. The important fact here is that the set of trig functions that we've derived, it's an infinite set. They're orthogonal to one another, and they're also complete. They're essentially L2 complete, which means that basically any function, okay, that satisfies being, C2 periodic, you can always express as an infinite series sum of these Fourier components. Okay, so so we'll finish this off on Wednesday. This should hopefully whet your appetite for the next topic in the course, which is showing how to